Today I'm going to be talking largely about the work that we've been doing in our lab and the Haptics and Medical Robotics Lab up on the Homewood campus, engineering robotic interfaces. I said for physical medicine rehabilitation, it's a little bit of a stretch. You'll see that some of the work that we do is kind of outside the PM&R space, but a lot of the work that we do is very clinically oriented and clinically relevant. I'll just kind of jump right in with kind of the formalities, objectives. Give you an overview of telerobotic devices, which are the class of robotic systems that we work the most with that generally involve human in the loop. Application of haptics in prosthetics. This is by and large the work that I've been doing for the longest. And then application of haptics in telerobotic surgery, which I said, kind of steers us a little bit away from PM&R, but I think some of the work that we're doing there, especially because of some of the collaborations that we have, will carry over into PM&R, especially in the motor learning space. And then I'll end by just kind of showing some of the late breaking things that we've been trying to get going and continuing to go kind of in the COVID era. In terms of disclosures, I really don't have anything to disclose. Kind of going forward with that. Okay, so to start off, it's probably, I don't have to, stress this to this audience, I know, but we use our upper extremity, our hands and limbs to do dexterous tasks of varying levels of complexity and difficulty in our daily life. Whether it's for hobby and pleasure or for work or what have you. We do a lot of complex movements with our upper extremity. I also probably don't have to stress to this audience that a large share of the reason why we can do such dexterous tasks has to do with the fact that we get nice sensory afferents from the periphery back to our central nervous system. And so the large share of my work focuses in on those sensory afferents, haptic feedback in particular, and why haptic feedback is important in robotic systems, especially robotic systems where you want the operator to have fine level dexterous manipulation and control capabilities. We know that haptics is important, but I'll just kind of show a cool video that I think is cool. You may have seen it already, that focuses in on just kind of why haptics is important from just a motor control perspective. There's a very old, video out of Roland Johansson's group. And what you're going to see in this video is a participant light a match, kind of in a standard, like you would light a match, pick it up out of the matchbox and striking strike the match on the box to light it, right? Then what they did is they applied local anesthesia to the fingertips of this participant and asked him to do the task again. You will see here that the performance looks significantly different. So, what can we learn from this, right? Well, one, there's a, you can see just, what the effect of just local anesthesia and the removal of some of these sensory afferents, these cutaneous tactile afferents do in terms of, being able to do fine level dexterous manipulation. The participant was still able to perform the task, right? A lot of it has to do with the fact that vision was still allowed, and we know that we are visually dominant individuals, and as long as we can visually estimate the scene, we can still reliably work and operate in the environment. I would argue that a lot of the robotic systems that we work with, the class of robotics, telerobotic systems, really are akin to this scenario where there is limited sensory, if any sensory afferent in terms of haptics, and mainly operated through visual, kind of visual servo and visual estimation of the environment. Okay, so let's kind of drive this into some of the work that we do. Well, we know that there are a lot of, even though we can directly manipulate objects in our own environment, there are a lot of environments where direct manipulation is not possible, either because the environment is located at great distances, it poses hazards to the body, it's on a different scale than our bodies are, or we've somewhat contrived ways of limiting access, as in the case of minimally invasive surgery. There are also scenarios where the body itself has changed. We want to be able to do the same types of direct manipulation that we do with our healthy, intact limbs in the case of amputation. Well, what we need in both of these scenarios is an interface. It takes the intent that we were trying to carry out on the environment and basically carries it out on our behalf. These interfaces were originally called teleoperators. Nowadays, teleoperators really don't exist except some niche scenarios. What we really have is a class of systems that I call telerobots, right? That allow us to operate at a distance. And in our lab, we like to think of an upper limb prosthesis as essentially a telerobot because you're operating this distal hand from more of a proximal location, generally through EMG. Okay. So, because these are robotic systems, we've done really well over the last decades of doing, great one-to-one mapping. Whatever motions you input into the system, the robot carries those motions out on the environment. Because these motions are, because these are robotic systems and they have a wonderful set of and suite of sensors, we can measure all of the interactions between the environment and the robot. But by and large, that information, this environmental interaction information, doesn't really pass back to the operator except maybe through vision, right? And so what my lab focuses in on is how can we add these haptic interfaces back to these systems in order to provide this particular haptic feedback to the operator. When you look a little bit more closely at this kind of haptic interface for these robotic systems, you'll find that by and large, the majority of it is not high fidelity if it exists at all. And so we are, our lab focuses heavily on understanding what is the right way to add haptic information into these telerobotic systems. When do you need it? When do you not need it? What types do you need? And the like, and kind of the whole spectrum around that thing. Just kind of as a case in point, right? I talked about two different telerobotic systems, or I should say I showed two different telerobotic systems, and one that we work with heavily in our lab, robotic surgery devices like the Da Vinci on the left, and upper limb prostheses, like the MPL that you see here on the right. You can imagine, both of these systems, wonderful control, amazing degrees of freedom. But a task such as simple as the one that I talked about before, taking a match and striking on the matchbox, is a difficult task even to perform with these complex robotic systems that mimic the same and have the same degrees of freedom as our natural limb, and allow the same level of control as our natural limbs do. These tasks are still, not trivial to perform. And so, again, to kind of drive home, this is where we think this is where my lab's interest and focus lies. Okay, so I'll kind of start off by talking about, a little bit of the work that we've done in the upper limb prosthetic space, as well as the work that we've done in the robotic minimally invasive surgery space. The work that I'm going to talk about in the upper limb prosthetics space has been done by my Ph.D. student, Neha Thomas, and alum of the lab now, Garrett Ng. And this is work kind of looking at and evaluating haptic feedback in upper limb prostheses. So, it's known, right, that even though despite all of the advancements that are being poured into prosthetic technology, especially upper limb prosthesis technology today, really they're true clinical options for most amputees right now. The body powered prosthesis, which we know is very old technology, post Civil War era, and then the myoelectric prostheses. And the differences between these devices, we can count them off there. I mean, there are numerous differences between these devices. We are, from an engineering standpoint, very interested in the body power prosthesis because when I started doing this work, we would talk to prosthetists, we talk to clinicians, we talk to amputees, and they would say, well, in addition to my body power device being pretty simplistic, easy to fix, and things like that, because of this nice bond cable that connects the prehensor to the shoulder harness that I wear, and get some inherent haptic reflection. And I can feel some of the interactions between, what happens with my prehensor. I can feel it in my shoulder through the cable. And so this was kind of anecdotally known, amongst, like I said, amputees, prosthetists, clinicians, and the like. And so I'm going to very quickly, and this will be the only experiment and results that I talk about today, take you back to a study that I did when I was actually in grad school at Michigan. And again, this is the only one that I've done. Everything else is going to be by my student. Or I should let you know that just in case anybody's checking attendance here, I did invite some of my students because by and large, all of this work was done by them. But a study that we did, when I was a grad student at Michigan, where we were interested in empirically evaluating the utility of this haptic feedback in body-powered devices, to see if we could, basically come up with an empirical result that matched this anecdotal data that we'd known for some time. And so, the problem with, trying to evaluate the utility of haptic feedback in a body-powered device is that you rely on that bound cable both for control and for the feedback. And so it becomes a little bit tricky to try and figure out how do you tease apart control from feedback. And so we kind of separated out and asked this other question: well, what happens if I remove the feedback part from the body power prosthesis? Does it lead to a degradation in performance in some, right, that hopefully involves some element of haptic feedback or haptic perception. And so you can, kind of going back to this, thinking of a prosthesis as a teleoperator, as we often do in our lab, it's essentially taking this inherent force reflection that you get from the device and removing it. Now, you can still do good control to the environment, but you don't get any of that interaction information back from the environment. So what I'm going to show you is a series of videos that we did to kind of go through the engineering process to be able to test this idea, test this hypothesis. So we started with, and this is a collaborator of mine who was in Michigan at the time. We started with this, kind of a standard body power prosthesis, as you can see in this video here, where you have the shoulder harness, bound cable connecting to a voluntary opening device. We changed the bound cable from connecting to a shoulder harness here to an exoskeleton that we mounted on the left arm here. And that was largely because the exoskeleton is a single degree of freedom device, and it was just much easier to control than something like the shoulder, which we know is a multi-degree of freedom joint. But essentially it's the same principle, right? Flexing your arm basically pulls on the bound cable the same way as it does with the shoulder harness. And then we just made the switch from a voluntary opening to a voluntary closing device. Because while you do get some haptic reflection in voluntary opening prostheses, it's really when the voluntary closing devices, where you can actually feel your grip force, transmitted through the cable, that we thought would be the most robust way to test this idea. So then, okay, now we've got this shoulder-controlled prostheses, right, or this exoskeleton-controlled prostheses that functionally works the same way as kind of the clinical variant. Again, the problem though remains, if I cut that cable, right, I've now, basically cut the ability to do control with the prostheses and feedback with the prostheses. And so what we decided to do is, okay, if we cut the cable, maybe there's a way, can we come up with a clever way of reconnecting them? And we decided to do it electromechanically. With two electromechanical actuators. So essentially it looks like this now. So you have two separate bound cables, one going to the elbow exoskeleton, one going to the prosthesis. And they basically aren't physically connected. They're connected essentially in software, and then through these electromechanical actuators that do the pulling on the respective cables. So basically what we do is we have a goniometer on the exoskeleton that measures the angle of the exoskeleton, and we use that and we map that to the prosthesis actuator. This little linear slide basically controls the pulling on the bound cable that opens and closes the prosthetic freehand. And so this is a video of this thing working, and so you can pay attention now. I don't know if my mouse is showing, but at least to these motors sitting on the table back here, to see exactly what's happening when the participant flexes the elbow. And so you can see that basically, even though the physical cables aren't connected, we still get essentially one-to-one mapping between the input position on the exoskeleton and the output aperture, let's say, of the prehensile. Now, what this affords us is the ability to turn the feedback off, because now all we have to worry about, because the exoskeleton has a bound cable connected to it, all we have to worry about is the tension in that cable, right? If we make that tension essentially zero, there's no force reflection. And we can control that by basically making the linear position of this exoskeleton actuator basically perfectly track the angle on the arm. So there's no resistance to the movement on the arm. So we can turn the feedback off. And then if we want the feedback to be back on, then all we need to do is basically monitor the tension on the prosthesis side, the bound cable that's pulling, that's operating the prehensor, and essentially proportionally map that tension to the tension that's on the exoskeleton. And so each of these has nice little load cells that measures the force or the tension in the cable on each side. And, in software, we basically just do a proportional mapping to make sure that the forces are exactly the same or some scale variation of the other. Okay. And so we can use an exoskeleton actuator to basically drive and produce force on the Bowden cable in the exoskeleton to produce the force feedback akin to what you would feel if it were also in the shoulder. So we ran this simple experiment. I won't go into too much detail, but we invited participants. These are all able-bodied individuals. So you'll notice that the prosthesis, again, had this nice bulge at the end, and that's so you could put your fist inside. An able-bodied or non-amputee participant could perform these experiments. We had the task was very simple. It was just object identification. So we had these little foam blocks. There were different stiffnesses, and you'll see this kind of repeated as a theme throughout some of the experiments that we do. And the foam blocks came in different stiffnesses. And all we asked the participants to do is basically squeeze the block and recognize it as being one of the three stiffnesses. We refer to them as soft, medium, hard, and basically sort them in the appropriate box, depending on their stiffness. And so the result that I'll just highlight really quickly is the one of accuracy. How accurate were they in the four conditions that we had? And the four conditions that we had were no feedback at all, so no vision and no haptics. Haptics only, so only force reflection on the exoskeleton. Vision only, so no haptics, but you could see everything. And then, of course, haptics plus vision. So these four conditions that we wanted to see our participants perform the task. And what we found is this, kind of, again, what we expected, kind of based on the anecdotal data, kind of data that we knew a priori going into this experiment. Basically, what we know and what we expect when you have, two pieces of information is better than anything else, right? If I can see it and I can feel it, you tended to perform better than all of the other conditions. At the same time, though, if you could only choose haptics or vision for this experiment, again, the task was object identification. So it was the task that relied heavily on being able to reason your force based on your displacement if you're squeezing an object to get its stiffness. But our results show that force feedback was better in this case than visual estimation of something like stiffness. And then, kind of as a confirmation that our no feedback case, was actually no information at all. It's just a shot in the dark. Without any information at all, you're basically guessing. You could choose one of three objects here, so the guess rate was roughly 33%, and that's what we found with no feedback. So this is kind of a result where we said, okay, let's take a clinical system, engineer it in a way that we can begin to test hypotheses with it. We were able to confirm, kind of empirically, that what we've been hearing kind of all along anecdotally from clinicians and amputees, was true. And so it's not an amazing, profound result because it was already well known, but at least we can say we've now got data and evidence to back this up. So I will kind of move on from that. And again, everything I talk about from now on is all work of my students. We know that body-powered prostheses are just, even though they have this inherent force reflection, they're limited. You generally get limited degrees of freedom, probably single degree of freedom, opening and closing of the prehensor. When you talk to amputees, they're not aesthetically pleasing all the time. You can't put nice cosmeses over them. They are simple and mechanical. So depending on what an amputee is doing, whether it's, kind of working out in the yard, they may prefer this device over something like, or where they're going to, maybe start to sweat, right, and start to mess with the conductivity with the EMG electrode. They might prefer this device. But, if we can continually improve, and the way the field is going is continually to improve myoelectric devices, that's the track that we're heading in. And our lab is going along in that direction as well. But as it stands right now, myoelectric prostheses don't have any haptic feedback. And so my lab is focusing in on how can we add haptics into these myoelectric prostheses. Everything that we're doing now is, I'll say, is non-invasive, kind of over the skin type of haptic feedback. So more of a sensory substitution type of haptic feedback. There are many labs out there that are doing either stimulation cortically or at the periphery, and we think I think that work is the future. I think what we're doing in our lab, and what I'll show you, is actually just trying to say, trying to better understand the science behind what is the right information to send, when do you need to send it, and how do you design and engineer your devices to be able, to better recognize in many respects when that information is needed for the amputee. Okay, so this next study I'm going to show you is actually some work that we've done. It's widely accepted in the field that when you add haptics as a sensory substitute to myoelectric prostheses, the performance gets better. We've had some studies in our own lab that have shown this result as well. here, what we were very interested in is, well, okay, we've done, as a field in the haptics field, we've done there are a number of studies that have shown this positive benefit of haptics in prosthesis. But by and large, clinical devices still don't have it. And so what's the bottleneck? Why, and so we, started to ask this question, well, one, how does this benefit of adding haptics compare to, let's say, a clinical prosthesis, so your standard myoelectric prosthesis, and how does it compare to, kind of the gold standard, our healthy intact limb? And so we set out to do this comparison between these three scenarios, our kind of lab-contrived prostheses with haptic feedback, your standard clinical prostheses, myoelectric prostheses without it in the natural limb, to see how these three, let's say, compare against each other. And we were looking at it from two different ways. One is just more of a task performance. So if I give you a task that involves something like force and requires force information to complete the task, and I give you that information back as haptic feedback, in this case, vibration feedback, because that's what we decided to use for this experiment, how well do you do? And then also we started thinking about, we know that it's known that vision carries a very high cognitive load. Well, if I add haptics in, does that reduce the cognitive load, or does that make it even worse now, because now you have to pay attention to this additional sensory cap, that's in this referred setting. So we wanted to look at what is the, cognitive implications in terms of processing of this additional haptic information in these three scenarios, in addition to task performance. So, what we have here, and I'll kind of walk you through, starting, maybe I'll go clockwise, starting at the top right. These three objects again, here they're all silicone now instead of foam, but there's still three different stiffnesses: soft, medium, hard. Visually look about the same. We tried to mask that still by wrapping them in, kind of black fabric, so you couldn't look at any visual imperfections in them. In the bottom right, you see, an image of the setup itself. You basically put your prosthesis through this little window and squeeze the blocks. That was the task, and you had to basically. We basically gave you two paired blocks, either a soft medium, a medium hard, or a soft hard, and you had to identify whether the first or the second block was stiffer. So kind of your standard two alternative force choice paradigm. And so, what we have on the bottom left, because we're using the impact hand, this is a piezo-resistive sensor, very similar to the work that Luke Osborne did in the T. Stackhor's lab. Where we can measure basically pressure on the finger. We put that same sensor on the end effector or the digit of the voluntary closing prosthesis. This is another mock prosthesis that we use in our lab. This one comes courtesy of Dankmeyer and Mark Hopkins group, that really helped us design this device. And again, we're measuring the forces at the at the digit, and we're playing that black as a vibration. As you can see here, this vibrotactile strap right below the bicep. And then in collaboration with a colleague of mine, Hassan Ayaz, who's at Drexel University, we've been using functional infrared spectroscopy, which looks at levels of oxygenation in the prefrontal cortex, and can tie that to cognitive load. I'm not going to pretend to understand all the science behind that, so I apologize if you eventually have questions about that, and I'm going to fail to answer them. We've looked at other modalities. EEG, of course, is another modality that's looked at for doing estimates of cognitive load. We've also looked at fMRI. Problem is, we can't use any of our electromechanical devices, next to a scanner. EEG just has a lot of, as you all, those who've used EEG before, it just takes a long time for setup. In terms of, gelling all of the electrodes that you want to use. So we decided to go with FNIRS. There's been some work comparing these modalities together, and FNIRS is reliable. Okay, so what did we find? So what you'll see here is that we got this kind of trimodal distribution. Basically, the response depended on what object pairs that we get. So soft, medium, medium, hard, soft, hard, which you can see on the x-axis at the bottom. That's just what the MH and S stand for. And those are the pairings. So I will kind of abstract this out for you and just focus in on the one in the middle, the soft medium. I can always try and answer questions about the other ones, but this is where we saw our strongest result. So basically what we found is that as we expected, right, the impact healthy limb, gold standard, perfect, right? I mean, 100% accuracy. 100% of the time, we gave you two objects, you were able to differentiate them. The clinical standard prostheses, the myoelectric without haptics, we had it around 50%. So guessing, essentially, right? We give you two objects and you essentially guessed which one you thought was right, and about 50% of the time you were correct. But then when we add the haptic feedback in, which is this like maroon wavy pattern block here, performance got significantly better, right? Clearly still significantly lower than what the hand is because the hand is perfect, but still, significantly better than what, the kind of standard clinical prosthesis is. And then when we look at cognitive load, the story is very similar, right? And what you're looking at here is just one of the optodes. So I think this is left medial. I believe it is. I believe it's left medial. I could be wrong. I have to go back and look at the paper again to be 100% sure. But what you're looking at is a change in oxygenated hemoglobin from baseline. So we took a baseline measure before the experiment started, and then we did a measure after the experiment. And what you see is that the natural hand, the solid blue, smallest change from baseline, right? So the task was not cognitively demanding with your intact hand. The standard prosthesis, very large change, significantly larger than the hand, which is this yellow polka dot. And then when you add the haptic feedback in, it actually reduces the cognitive effort, right? So, we were kind of, we hypothesized that it would, but we were also aware that there was a chance that having to process this extra information would basically increase cognitive load, because now you have to pay attention to this extra channel of information. But in this case, it seemed to reduce the amount of cognitive effort, at least compared to the standard clinical prosthesis. Still very, high, significantly higher compared to the intact hand. But it means that we're going in the right direction at least. And so there's a lot of efficacy and utility in, haptic, feedback, whether it's, sensory substitutes like we use, or direct peripheral, like a lot of other labs looking at, has a lot of great potential utility in improving, kind of the function for prosthesis. Okay, so I'll wrap up, kind of with that. I've got one more thing or two more things that I'll show you in the prosthesis space that are kind of late-breaking, ongoing stuff. So not a whole lot of results to really talk about just yet there, but I'll at least show you the setups later on. I'll jump into the work that we've been doing in robotic minimally invasive surgery. Again, the first project that I'll start with literally has not a whole lot to do with, I would say, the PM&R space, but I'll get the next study is starting to track in that direction. So anyway, as I mentioned before, the Da Vinci robot, which many of you may know about, right? It's a great robot. It's used all the time in the surgery department, especially for general surgery, urology, gynecology. But right now, as it stands, all surgeons are operating this device without haptic feedback. So it's all visual feedback, at the moment. And so while expert surgeons learn to account for this lack of haptic feedback in their motor plan, novice surgeons, have a very steep learning curve when trying to learn how to use this device. And so what we were very interested in is, well, can we use haptics as a way of speeding up training for these novice surgeons on these complex robotic devices? And so what we have is a simple setup here where we put kind of a standard inanimate task, this ring roller coaster task. So the objective is to move the ring along the track, and not let it drag on the track at any point. We put that on top of a force sensor. And so we can measure all of the interaction forces now as you're doing this simple task. And then we take that force and we map that to these little these little simple wrist-worn tactile devices, which basically, essentially, you think of as a wristwatch, where the harder you press on the task, the larger the force you produce, the tighter we squeeze the strap around your wrist, right? So it's a proportional mapping. You sense force and you produce basically a squeezing kind of pressure on the wrist. And so we had this simple task where we basically asked participants to do this experiment over and over again for about 12 trials, because we wanted to look at learning over the course of these 12 trials. And we compared that to kind of the control condition, or the natural learning condition, where you didn't get any haptic feedback. You just went and did the task repeatedly over and over and over and over again. And so what we found is that and you're looking here at essentially a log transform of the RMS of force. So we measure the force over the entirety of the trial, compute the root mean square of it, and that's what you're looking at here. And these are the results of the linear mixed model, which basically say that with the feedback group produced significantly less force than the no feedback group over the entirety of the trial, all 12 trials, significantly lower force. They started off lower and continued that way, for all 12 trials. And so we were saying, that was kind of a nice, like, yay, okay, haptics really works. It leads to improved performance here, because forces in this case are generally a bad thing, because they come from either directly contacting the track or pulling the ring on the track itself. And so the lower the force, that means the more the ring is in the center, or the track is in the center of the ring, and so you're freely moving it in space. And so it seems like adding haptics in, right away. And these were all, let me just back up really quickly and say, these were not clinical participants. These were, basically participants that we, largely undergraduate population, non-clinical, but had never used a Da Vinci before. So it came in for this experiment just to use a Da Vinci. And what we see is that compared to a natural learning, they produce less force. We were then saying, okay, well, what does this mean in terms of kind of a speed accuracy trade-off, in terms of how long it takes them to do the task? And so now I'm starting to go into more of the motor learning. Here, we didn't actually we didn't force them to change their plan. We were just saying, okay, how fast do they go? And what we found is that, kind of as expected, when you get this haptic feedback, it's extra information to process, and it takes you a little while to get used to processing this information. And so you start off slower than you do in the no feedback condition. But, trial after trial after trial, participants in the feedback condition got faster, right? And in fact, they got faster at a significantly faster rate than participants in the no feedback group, in the control condition. Now, if we carried this out for an additional, let's say 8 trials to get to 20, what would have happened? I'm not 100% sure. Would they, essentially get to a point where they're no different from one another? That's yet to be seen. Or would they just plateau exactly where they are? But at least we can see that even though there's like an initial penalty for adding these haptics in, within 12 trials, and each of these trials was like 30 to 45 seconds, participants just got significantly faster and faster, which is, I think, not, mind-blowing, kind of result here. Just repeatedly doing things over and over, you're just going to get better and better and better at doing it. But they did this, they got faster while also keeping their forces significantly lower. Okay. One other study that I'll show is some work done by Guido Castianiga, who's a visiting student of mine, and this is actually in collaboration with Gabriela Cantorero, some work that we did also in the surgical training space. And this, Guido was a visiting student of mine, in my lab for about 6 months from Italy. He's now a Ph.D. student at the University of Stuttgart, and he's affiliated with the Max Planck Institute in Stuttgart, Germany. So anyway, Guido kind of came in with this idea that, like, hey, when I look at surgical robotic training, they're kind of 2 different flavors, right? There's VR training, right? So they've got these desktop trainers, as well as the Da Vinci itself comes with this nice little DVSS or Da Vinci surgical simulation pack that you can put on and, kind of VR, practice all of these different things. And then, you've got actual training on the real robot itself. So inanimate tasks, excised tissue, animal models, cadavers, things like that. By and large, when you talk to clinicians, a lot of times they will say, well, the real robot is still the gold standard. There's some, empirical evidence to back this up that says that, hey, training on the real robot, you actually learn to incorporate and understand the dynamics of the robot itself in your, let's say, control of the system. And so we kind of said, okay, well, from a training perspective, are these 2 systems equivalent? And so what Guido set out to do is basically build this virtual and inanimate analog of the same training task. So what you're seeing here on the left-hand side, and this is a video and I'll play it in a second. All right, maybe I'll start on the right-hand side, but that's where it originated from. Guido built this inanimate needle driving platform. So it has these 3 rings that are basically spaced 45 degrees from each other, one at, I would say 0 degrees, and one at 90, and then one at 45. And the objective is to take a suture needle and drive it through the rings without deflecting the rings in any direction. Then what Guido did, and the rings do have visual feedback. So they do LED lights that go around that light up depending on how, the error that you produce, and the intensity of the light, and the location changes on the deflection of each of these little individual rings. Then what Guido did is he took his 3D models that he built for this system and converted it into these like nice 3D meshes in a VR simulator, where he basically has the exact same system in a VR environment. And he can control it, both the physical system and the VR system, from the same interface. The DVRK here, which is the Da Vinci Research Kit robot, which is an open source version of the Da Vinci robot that we have up on the Homewood campus. all various studies related to robotic surgery. So I'll play this video. These aren't exactly the same, so they're not going to be time locked, but you can get an idea of how you can take the same interface or the input from the human side and drive, either the virtual environment or the real tools in the physical environment. And so you can kind of get the coloring on the right-hand side. This is actually taken from the viewpoint of the robotic endoscope, which is why the color is not perfect, and it's got this nice little green tint to it. So essentially, what we did is we ran a study where we had, basically two groups of participants, A and B, and we asked every participant to do a baseline measure of their performance in each of these respective platforms. IN stands for inanimate or the real world. VR, of course, is virtual reality. So 15 repetitions of the task in each of these platforms. Then we did training in each of these tasks at 3 different speeds, slow, regular, and fast. And I'll talk about that, the reason for that a little bit later. But basically, we gave them a chance to do 40 repetitions of the task now on the same platform. If you started doing baseline on inanimate, you stayed on inanimate for training. Same thing for VR. And then we did an evaluation. 15 repetitions of the same task on that same platform. And so we wanted to see, did performance change from baseline to evaluation because of the training block that happened in the middle? And then as a final step, we did what we call a cross evaluation, where if you did all of your baseline training and evaluation on the inanimate platform, we then swapped you and you did a cross evaluation on VR. Likewise, if you did baseline training evaluation on the VR platform, we swapped you and you did a cross evaluation on inanimate. And so what we found is that, again, we got this trimodal distribution. I'm only going to talk about the moderate speed because that one is most reflective of kind of natural training speeds, what, kind of a participant would do. Fast was like kind of faster than you would like to do, slower or slower than you would like to do. And this is because of work that we were doing with Dr. Ken Torero, in terms of trying to understand the speed accuracy function. And so, but by and large, if you just look at one speed, what we see is that in both platforms, so going from the red box whiskers to the green, there was a significant decrease in error. So what you're looking at on the y-axis here is the performance metric, which is essentially an integral. We basically took the total displacement of all 3 of those rings over the course of the experiment and just computed an integral of that over time. So this is a representative of the total displacement of all the rings. And so the lower the better, because essentially ideal perfect would be no displacement of the ring, so 0. And so what you see here is that from red to green, participants on both platforms got significantly better. They lowered their errors. But then when you go from the evaluation on one platform to the cross evaluation on the other platform, what we found is that in the inanimate the group, which is the left-hand plot here you see, there was not really a significant change from doing the evaluation on the inanimate platform and then doing the cross evaluation on the VR platform. So no significant change kind of in error. But then when we look at the right plot here, going from evaluation on the VR platform to cross evaluation on the physical platform, we got a significant increase in error. And so what we're starting to think about this is that something about doing the task in the physical environment grounds the skill a little bit differently than it does in the VR environment and allows for better skill transfer. So you can transfer the skill from, you can transfer the skill better from physical to the VR world than you can from the VR world to the physical world. And so, we still have much more data to analyze in this case, but, I think this is starting to piece together a picture that, we've kind of been thinking about a lot in our own work, is that, it kind of backs up this idea that the physical robot is somewhat the gold standard, because there's something about grounding it, in at least when you're trying to develop this skill in the physical world, as opposed to grounding it in, let's say, kind of learning these skills in the VR environment. Because if you learn them in the physical world, you can transfer it into the VR environment. But if you learn it in the VR environment, it doesn't transfer as readily back to the physical world. Okay. So now I'm going to add a third category here really quickly and just talk about some work that we've been doing in fundamental haptic perception. So just trying to understand how we perceive the world through our sense of touch. And this is some work that's being led by my graduate student, Mohit Singala. So Mohit's been working largely in this area around haptic perception, and he came up with this idea, when we think about, perception with one hand, or perception with two hands, do we perceive the world differently when I'm interacting with one hand or two hands, right? Are two hands better than one? If I perceive the object with both hands, does the percept that I develop of that object, is it more robust than if I only felt it with, let's say, one hand, right? So, kind of think about this. Imagine I have this little cube, and I ask you to fill this cube with your left hand, right? Is your perception of this cube different than if I ask you to perceive that same cube with your right hand? Likewise, if I have this cube and I ask you to perceive it with both hands together, what is the perception of that cube now? And how does that differ from either of these unimanual conditions? So what Mohit developed in the lab is a simple, a single degree of freedom haptic interface, but very robust in terms of like what we can do with it. It just consists of a motor and encoder and this little hand fixture that has this kind of alternating finger pattern, to kind of make sure that all the motion that we're getting is really, in this case, pronation, supination, or wrist rotation. What we can do with this device, as I mentioned, is that we can basically make it render any physical environment that has some inherent dynamics and mechanics, right? So a spring, for example, if you follow a Hooke's law formulation, just says that the torque of the spring is equal to some constant K times the displacement on that spring. And so what we can do, as you can see here, is take that same displacement and produce, by changing the variable K, a different torque output. So imagine here, the kind of simple example is, you've got a doorknob and you're turning the doorknob, and in between your turn to the doorknob, I'm basically taking the spring out and put a stiffer spring in, so you get a different force or a different torque output as you turn the doorknob. We can physically do that in the virtual environment just by changing or putting this parameter K. So for the same displacement, you basically get a different torque profile from your spring. And so what Mohit did is he built this setup, and he has a duplicate one, so you can actually do two hands now. And basically what happens now, you can displace that spring, with one hand, you can displace it with the other hand, or you can displace it with both hands. And so the both hands is a little bit hard to kind of think about, but imagine now, maybe let's step away from the rotational world and just go, imagine that I gave you a big spring to hold in both hands, right? You can pull on that spring like this, and you would feel the spring pulling both of your hands back together. Imagine it was just a rubber band, right? That rubber band would want to pull your hands back together. If you pull with this hand, right, it would want to make, you would still feel the force, the resulting force in both hands as it tries to pull them back together. Likewise, if you pull with this hand, it would try to pull them both back together, right? And that's essentially what we've done, except in a rotational domain now. If you rotate with this hand, you feel the resulting torque in this hand. If you rotate with this hand, you feel the resulting torque in this hand, because we've mapped it now to the total displacement of both ends of the spring. And so we ran a psychophysics test, a method of constant stimuli, where we basically varied the change in the parameter K, because we were trying to estimate the just noticeable difference in these three conditions: left unimanual, right unimanual, and bimanual. This is just one of the psychometric curves from a representative participant here. And what we found largely was that, now this is a majority right-hand participant pool, that actually their left hand was perceptually more sensitive, right? So even though these were largely right-hand dominant participants, I think we had only one participant in the pool that was left-hand dominant. They had lower J&Ds, so higher perception, higher sensitivity with their left hand. And then bimanual kind of fell somewhere in between left and right. We're still analyzing this result. Still as we prepare for submission. But it is starting to piece together this idea that, yeah, there are these asymmetries perceptually between the different sides of the hand. And how we piece this story back together bimanually is very, very complicated, right? It's not just simple as, oh, well, I only trust information from one hand or the other, because there's been work that's been looked at in terms of visual haptic information. And if you distort one channel, you tend to rely on the other. Here, it doesn't seem to be this kind of optimal integration that we would expect as like you see in the visual haptic domain. And so we're still trying to work out, as engineers, non-neuroscientists, kind of from behavioral studies, what's really going on in these bimanual conditions. And we've got some other experiments lined up where we're trying to really tease apart and break down kind of into its constitutive parts, something like stiffness and what that really means. Okay, so that's kind of the last of all of the work that we've done where we've got actual results to present. Everything else that I'm going to talk about is kind of a post-COVID or intra-COVID maybe era where we're still building systems and starting to get some preliminary data. With the exception of this one, I apologize. So remember I showed you the study that we talked about where it was comparing virtual reality training and inanimate training. What I was showing you in that result that we presented was actually only the results of a sham group, right? So in that study, Guido actually ran an additional cohort where we applied transcranial direct current stimulation and did the exact same protocol. And so we are in the midst, and Gabriella, I actually just had a conversation with Guido today, and he's like, I'm going to start working on it right now, because I think the whole EU is getting ready to go into a severe lockdown. So he's got a lot of time on his hands. But analyzing essentially, the differences, we started and we will finish now analyzing the differences between the sham group and the stimulation group in terms of what effect that TDCS, have on performance. So my student Mohit and my student Teresa have also been working with Gabriella and everyone else has been working, with this collaborative effort between the hospital and APL and Buzz on more of a scientific experiment where we're looking at sensory motor attenuation. And so Teresa and Mohit have put together this experimental setup, which I'll see, and you can see Buzz using it in the left-hand figure here, where we're looking at, a self-derived stimuli versus stimuli that are not self-derived. We derive them ourselves, and what happens in terms of sensory motor attenuation. So you can see this little setup here. You press your hand, there's a little force sensor that measures the force, and we basically, this is essentially a telerobotic device. You input force and we output force with our little simulator, and we can actually measure it on the other side. And so this is a simple setup that we're using now to run some experiments to investigate sensory motor attenuation. And we get to do that alongside nice cortical recordings because Buzz has been implanted with these intracortical electrodes. My student Sergio Machaca and my former student Garrett Ung have been working on this experimental setup. So everything that I showed you kind of in the haptics for telerobotic space has largely been single modality type of feedback. Right? We measure force and we either produce that as like squeezing or vibration, but it's still just one piece of information. We know that you've got a suite of mechanoreceptors embedded in your fingers, right? And you've got other sensory, receptors, in the musculoskeletal apparatus. So we get a lot of haptic information all the time. And so we started thinking about, well, can we start giving more than one type of haptic, piece of haptic information? So this simple study here is looking at two modalities of haptic information. And what you see here is a simple experiment, all virtual environment right now, where you have this virtual object, and the task is to basically grip the object and keep it from slipping. The difference, though, is that you see this little long tail on the object. What we do virtually is, you can think of it as like taking a string connected to this object, and while you're holding it, we pull down on it. So it's almost an analog to like the grasp and lift paradigm, except here it's just grasp and hold, but we modulate essentially the lift or loading forces on the object. And what we're doing is providing participants with haptic feedback of their grip force, which you can see on this wrist, the wrist squeezing device that we talked about before, as well as information about incipient slip. So if the object starts to slip, we basically map the velocity of slip to this vibrotactile actuator that they're wearing on their arm as well. So they've got two pieces of information, their grip force and then slip indicator. And we want to see how well they do the task. And we have now look at this from two kind of interaction paradigms. One, it's kind of physically manipulating a gripper like you would find on a Da Vinci, and that's what this little gripper on the bottom left is modeled after, is a Da Vinci style gripper. And then the other is more of more geared towards prostheses with the EMG, where you now have antagonist EMG electrodes that allow you to basically control the grippers like you would the prehensors of a prosthesis. We don't have any actual data to show on this just yet, so I'll at least show you a video of how the setup is supposed to work. Oh, and I should mention these objects are also brittle. So imagine now that the object is actually an egg, where if you squeeze too hard, you could break it, which just happened right there. And you'll notice we remove visual feedback. Again, we tend to be visually dominant, and so we wanted to see what would happen just based on just getting the haptic information back. A little bit contrived, but it allows us to test what is the utility of the haptic itself. So this is some work. The only data that I've collected, kind of since the COVID shutdown, has been because I have a student, Neha, who's in Germany right now at Max Planck on a Fulbright fellowship, and because Germany just handled things a little bit better than we did, they could run studies for the better part of the fall. So she's been working on some experiments looking at combining haptic feedback, which we've been doing in our lab for prostheses, with things that, some of the advancements that have been taking place in the industry, these automated grasp controllers, right? So these controllers that basically, if they sense the object slipping, they'll just grip tighter. And so we are wondering, kind of in this shared control strategy, what if you added haptics on top of this more intelligent type of controller on your prosthesis? Could you get better performance out of your prosthesis? So she has this mock prostheses that she's developed in Germany, which is using the Autobot sensor hand, I want to say, our speed. I can't remember exactly what the model number is, the model is, but the task is fairly simple. It's grabbing an object out of one bin and placing it in the other bin. The only difference is they force their participants not to look at the task. So you had to stare straight at a wall and basically use, in this case, your haptic feedback. So what you have is on one digit, you have a contact location sensor that basically will tell you where contact was made along the length of the finger. And then on the thumb, in this case, you have a pressure sensor that tells you how much pressure you're generating. And we're giving them haptic feedback of both pieces of information, so that you can kind of recognize where you're grasping the object and then also how hard you're squeezing the object. And then, like I said, we compared that to a case where you don't have any of this information. And then also with the haptic feedback, we added on this grasp controller. So if the object started to slip, the grasp controller would kick in and make, and force the prosthesis to squeeze a little bit harder on the top. For the video that I'm going to show you next, it's a little bit long. I apologize. I didn't really know the right place to trim it, but you're going to see 4 different videos. One is going to be the no feedback condition, an unsuccessful trial and a successful trial. And then you're going to see the hybrid condition with haptics and the automated slip controller, and partially successful and a successful trial. And then what you'll see is kind of this 2 side-by-side video. One is the side view from the camera that's looking at the experiment. The other is actually they had the participants wear eye tracking glasses, so you can kind of see where their focus is over the course of the experiment to kind of show that they're not paying attention to the task that's happening down below. So now this is with the haptics turned on and the automated grip control. Right. And this is one where no feedback, but the participant was still successful because we thought it was kind of worthwhile to see that you can still be successful even without the feedback. And this is the final one with the feedback on and the automated controller on. And this is participant is successful all the way. And so, I won't have any data to really show you, but I can tell you kind of our results thus far show that the benefit here that we're finding of the haptics and the automated controller right now is that it reduces the variability in performance. So participants just perform, they're more successful than they are. We've got some there's some stellar participants with no feedback who are able to do it. And they all have these like, when you ask them what strategy they were using, there's these like kind of I don't even know what you would call them, but intricate strategies for trying to figure out where the object is and come up with some representation of the object to know they have it. Whereas when you talk to the participants that were using the haptics, it was essentially I was relying on the feedback to tell me when I had localized, right? And so this task seems a little bit brutal to put participants through, right? But this task is representative of many situations where you can't directly look, right? So if I ask you to reach in your pocket and pull out your keys, right, you don't have visual access to that, but it's something you can do seamlessly, right? Or if I put a bunch of coins in your pocket and told you to get me a penny and a quarter, or separate, find the penny or find the quarter, you would easily be able to do that just kind of based on the size of the object without directly looking at it. And so this is something we kind of take for granted, that in amputee kind of in their current, instantiation of prostheses wouldn't be able to do. And so we're trying to think about ways to explore this empirically. Okay, some other prosthesis work that we've been doing. This is some work by my former student Ethan Miller and Himri Rochi, who was actually a high school student working in the lab. This is a newer prosthesis that we developed, also in collaboration with Mark and the folks at Denkmeyer, where instead of being, kind of a single motor in the hand driving open and closing, we decided to use two antagonistic tendons to do both flexion and extension of the hand. And then in addition to that, we have this haptic feedback system that's kind of embedded within the cuff itself, of the socket itself, which we're hoping to provide, kind of real-time feedback of what the tension is on either side, because we know that, based on how I co-contract my muscles, I generate different, endpoint stiffness and impedance of the limbs themselves. And it's been shown, there's evidence to suggest that we modulate our limb impedance for various types of tasks, and so we're interested in exploring that kind of possibility with a prosthesis. And so this is kind of the first prototype of this device that we've worked on. Again, all of this happened right before COVID, so we haven't really done much with this since, but I can at least show you this video of how we control it and then kind of functionally use it in like a simple box and blocks task. And I'll skip past this. This is long. Really quickly, I just want to show you some work that we've been doing in collaboration with John Krakauer's group in the BLAM lab, and now Jing Xu and her lab, the Codex lab at Georgia, working on, this is some work by my student, Jacob Carducci, who really helped with a lot of the engineering around the hand device that John and Jing have been using in some of their experiments. And now Jake is working, taking the device that Mohit built, and we're starting to look at, assessing sensory impairment post-stroke, kind of using robotic means. And so kind of a lot of the work that we're doing in haptic perception and, kind of the basic fundamental stuff that we're doing in haptic perception, trying to apply that to basically trying to better understand sensory impairment after neurological disorder or disease, like and then last is some work by my student Mohit, who's doing exploring, this is kind of a simple telerobotic interface where we're trying to see what impact the dynamics of the telerobot have on perception of the remote environment. And so I won't go too deep in that because I didn't give a nice primer for it. But basically, this is a single degree of freedom teleoperator test bed of sorts, where we can modulate what are the dynamics between both sides of the teleoperator without affecting what happens on either end of the teleoperator, and imagine what impact that has on you. Okay, so with that, I just stop here. That was my last slide. Acknowledge all the work of all the students in my lab who've done the lion's share of this work, and I didn't even get a chance to talk about everyone's work, unfortunately. But I want to thank them for all their hard work and effort. And then if you wanted to learn more about the work that we're doing in our lab, here's my lab website. You can easily go to the website and, get in contact with us if you wanted to learn more. And yeah, I'll just stop right there and take questions.